What are the best methods to balance DC-DC converter transient and steady state? Imagine trying to keep a boat steady on choppy waters while also sailing smoothly on calm seas. That's similar to what engineers aim for when designing DC-DC converters. These devices switch power on and off rapidly to regulate voltage, but balancing quick responses to sudden changes with stable operation during normal conditions is a real challenge. So, how do they do it? Let's explore the methods that make this possible. First, the control loop is the heart of balancing transient and steady-state performance. By adjusting how fast the converter responds to load changes, engineers can improve transient response. Increasing the control loop bandwidth makes the converter react quicker, but too much bandwidth can cause instability. To prevent this, maintaining a phase margin above 45 degrees is essential. This margin keeps the system stable and avoids oscillations during sudden load shifts. Adding a feed-forward capacitor in the feedback network can also help by boosting bandwidth, allowing the converter to respond faster without losing stability. Next, component choices play a big role. Larger output capacitors help smooth out voltage ripple during steady-state operation and absorb transient energy when loads change suddenly. Low equivalent series resistance capacitors are preferred because they charge and discharge quickly, improving response times. The inductor value influences how fast current can change. Smaller inductors allow quicker current shifts but can increase ripple. Proper input capacitors are also important. They prevent input voltage ringing that can affect both steady-state and transient performance. Advanced control techniques can further improve balancing. Hybrid control schemes combine pulse width modulation with hysteretic or other fast response methods, giving quick reactions without sacrificing efficiency. Feed-forward methods inject a preemptive signal before a load change, reducing overshoot and undershoot. Adaptive compensation dynamically adjusts the control parameters based on load conditions, optimizing performance in real time. In applications like renewable energy systems, these methods are vital. Solar inverters and battery management systems need to respond swiftly to changing inputs while maintaining stable output voltage. For example, when sunlight varies or batteries charge and discharge, the converter must adapt quickly to keep electronics safe and efficient. In summary, the best ways to balance transient and steady-state in DC-DC converters involve designing a well-tuned control loop, selecting the right passive components, and applying advanced control strategies. Proper bandwidth, phase margin, and component choices help achieve quick responses and stable operation. These techniques are key to reliable power systems, especially in renewable energy and sensitive electronic applications.